This rocket that I built has an active control system. It has a custom flight computer in its nose, and it uses these 4 aft fins to steer itself through the air. This rocket has flown 5 times now, but only 2 of those flights are up on the channel. Today we're going to talk about the last 3 launches, flight tests 3, 4, and 5. All of these launches were testing waypoint guidance. We're going to give the rocket a coordinate in the air, and it's going to try to fly to it. But before we talk about any of that, we need a little bit of background. What am I doing? Why am I doing it? And what happened on those first 2 test flights? I had 2 goals for the Diamond X program. First was to show full aerodynamic control of the model rocket and to improve over some of the previous rockets that I'd built. Both Diamond 1 and Diamond 2 used canards to try and steer, and this layout has a number of problems. Just like the AIM 9X, Diamond X changed to a tail control design to solve some of these controllability issues. My second goal was to demonstrate some unique types of guidance, steering the rocket to waypoints or along paths in the sky. Doing these modes would be a huge technical challenge, but they would also let me put some of that academic control theory into practice in real life. The end goal for both the waypoint and path-following guidance modes is to try to fly the rocket both upwind and downrange to help the rocket recover to a safe landing site under its parachute. So what has this rocket done so far? Flight 1 tested the rocket's Euler angle control system. I commanded the rocket to fly straight up and included a 45-degree roll program. This worked almost flawlessly, and a video for this flight is out on the channel. Flight 2 was all about testing Diamond X from the Atlas hot launch silo. The rocket was loaded and held by the metal rails in the silo, and its rocket motor was ignited. This is some of the coolest launch footage I have ever taken. In flight, the rocket executed a pitch program, pitching down to 20 degrees below vertical and back upwards. This worked pretty good, but it could have been more maneuverable, especially at high speed. This launch also damaged the silo, so that entire thing's going to have to get rebuilt. And that leads us to today and flights 3, 4, and 5. Okay, so before we talk about these last 3 flights, we need to talk about some background on what these rockets do and how they work. On board Diamond X, there are 3 important systems. They are the guidance system, the navigation system, and the control system. As I've discussed before, the navigation system tells you where you are, the guidance system tells you where you want to go, and the control system actually gets you there. Now, I refer to these as guided rockets, where others will describe them as a rocket with an active control system. To be very clear, these are kind of the same thing. If your rocket has an active control system of any type, it has to have some guidance system, even if it's very simple, telling the rocket where to go. Most amateur rocket guidance systems are trying to control the rocket's attitude, or where it's pointing. The most common one of these, and probably the safest, is point the rocket straight up. This keeps the pointy end up, the flaming ends down, and gives you the best chance of safely recovering your rocket. There are also some very talented people out there who have landed model rockets propulsively, and this is a very, very difficult guidance and control problem. Questions like, when do you ignite the landing motor, and how fast should you be going at a given altitude, are things that the guidance system has to figure out. A lot of the work that I do on this channel is implementing interesting or novel guidance systems. Diamond X flights 3, 4, and 5 tested one of these new systems. Now, confusingly, Diamond X actually has 3 different guidance systems that are active at different times during its flight. So to help all of the flight footage make sense, we're going to go over what those 3 different systems are, how they work, and what triggers the guidance mode to change in flight. Guidance modes 1 and 3 are both variations on Euler angle guidance. This is a type of attitude guidance system that takes pitch, yaw, and roll set points and tries to have the rocket achieve them. The first mode to talk about is launch direction hold. On launch, the rocket isn't going fast enough to do any fancy guidance modes, and we also need to calibrate some parts of our control system. When we're trying to fly to waypoints, this is the mode that's active as the rocket leaves the rail. It tries to point the rocket straight up and get its roll under control. To change guidance modes, the rocket checks its roll angle and its roll rate. If those 2 values are within certain thresholds, it means we've got the rocket stable and we can transition to waypoint guidance. Before launch, the rocket is assigned a waypoint. These are coordinates relative to the launch site and include a position and an altitude. I can choose a waypoint that is both upwind and downrange, both to shorten our recovery distance and to keep the vehicle away from all the people at the launch site. This waypoint track is assigned remotely via the data link. Without a track assigned, the rocket will fly a pre-programmed pitch, yaw, and roll profile that's stored on the onboard SD card. If I have assigned a waypoint, the rocket will try to fly to that waypoint instead. Diamond X tracks its position with its onboard inertial navigation system, and it tries to fly as close as possible to this waypoint. The rocket compares its position and its velocity to the position of the waypoint and generates lateral acceleration commands. Several other pieces of guidance and control software translate this into fin deflection angles. When the fins deflect in pitch or yaw, it rotates the rocket to some angle of attack. This makes the rocket's body generate lift, and this lift is the force that causes our lateral acceleration. When the rocket detects that it's past the waypoint, it changes guidance modes for the last time to Guidance Abort Euler. This is almost identical to the Launch Direction Hold mode, trying to point the rocket straight up and control its roll. Unlike Launch Direction Hold though, this mode is permanent and the rocket doesn't look to change modes again for the rest of the flight. After mode change, the rocket will also start reporting its closest approach or its miss distance over the data link, so even if we lose the rocket, we can tell if the guidance and control system worked. We point the rocket straight up at the end of the flight to make parachute deployment easier. We want to deploy our parachutes while the rocket's going as slow as possible to minimize the shock loads of the parachutes deploying into the airstream. As we approach our apogee, our vertical velocity goes to 0, but our horizontal velocity stays constant. If we're going too fast when the parachutes deploy, the shock cord or parachute attachment might snap. The Abort Euler guidance mode tries to minimize that risk by keeping our rocket traveling straight up at the end of the flight. Now, there's actually a second reason the rocket might go from waypoint guidance to abort guidance. If there's any mistakes in the waypoint guidance algorithm, the rocket could spiral out of control and come careening back down towards the ground. Obviously, this is very unsafe, so waypoint guidance has a built-in failsafe. If the rocket's pitch or yaw angle ever exceeds 40 degrees, the safety system will automatically switch the rocket to abort guidance and will stop trying to fly to our waypoint. Now, I'm never going to set the rocket's waypoint at such a low angle on the horizon, so the only time this system should trip is if there's some fault in the guidance system. Right? This is foreshadowing for later. The last thing I'll mention is that you'll see the control system turn on about 20 meters in the air. This gets the rocket up and off the rail before any of its fins start to move. When we watch the flight footage, you'll also be able to see what guidance mode the rocket is in. When those modes change, you should be able to see the rocket's behavior change. Okay, that's enough diagrams. Let's talk about these last 3 rocket flights. Flight 3 was my first attempt at doing waypoint guidance. A waypoint track was assigned upwind and the control system was checked. We got ready to launch.
5, 4, 3, 2, 1.
The rocket lifted off in launch direction hold mode and stabilized its roll. It transitioned to waypoint guidance successfully and did absolutely nothing. It just followed a ballistic path straight up until it was above the waypoint, and then it transitioned to abort guidance and recovered successfully. So it turns out I had forgotten a single line of code, and this had paralyzed the entire guidance system and left the rocket commanding 0 lateral acceleration. I'd done some last-minute tweaking to the guidance algorithm and didn't ground test that, so that's on me, I guess. Well, okay, so the waypoint guidance didn't work, but all of the mode transitions worked really well. So we did a little bit more ground testing, fixed that problem, and then it was time to try again. Flight Test 4 was a very similar setup. A waypoint 40 meters downrange and 650 meters in the air was assigned via data link. Given that at this point the whole waypoint guidance and acceleration control systems were totally untested, success here is getting within like 10 meters of the waypoint. I would be ecstatic if we got that close.
5, 4, 3, 2, 1.
There it is out there. It reported a 0.3 meter miss distance from its waypoint. Let's go see if that's real. That would be nuts if it was true. Its actual miss distance was only about half that far. After liftoff, we can see the control system enabling and launch direction hold getting the vehicle under control. At 127 meters in the air, it transitions to waypoint guidance and it pitches downrange. The distance to the waypoint comes down with acceleration control working really well. 6 seconds into flight at 70 meters per second, Diamond X passes the waypoint 15.6 centimeters off the rocket's right side. After passing the waypoint, the guidance mode changes to abort oiler and Diamond X pulls up to vertical. At 828 meters in altitude, 12.5 seconds into flight, the rocket reaches apogee and deploys its parachutes. Okay, so this flight had a miss distance of 15.6 centimeters. That is an order of magnitude more precise than I was expecting it to be. But does that mean that Diamond X has a 15.6 centimeter precision? How do we even measure the precision of a vehicle with a guidance and control system? So this topic is actually very complicated, but the short answer is no. We can't say that Diamond X has a 15.6 centimeter precision, and we can't authoritatively say any other number either. Precision is a probabilistic process, and our understanding of that process is limited by statistics. As a probabilistic process, a rocket's ability to fly along a path or to a certain point is a variable with some distribution. The rocket may go here or here, but it's most likely to go where the probability is the highest. The width of this distribution is related to our precision. If this is a normal distribution, we can describe its width with sigma values or with standard deviation. The lower these values, the more precise the rocket is, but on any given flight, it may have any miss distance. Another way you may see precision described is with CEP, or circular error probable. In this case, this value describes the radius of a circle around our waypoint. If we launched Diamond X 100 times, it would pass the waypoint inside of the circle 50 of those times, and it would pass the waypoint outside of the circle the other 50. Again, the smaller the circle, the more precise the rocket is. No matter whether you're measuring with circular error probable, or standard deviation, or any other probabilistic metric, you need to know what the value of that metric is. To find these values, we have to collect data. We need to launch the rocket a whole bunch of times, collect some miss distances, and then do some math on that data set. This math will also tell us how confident we are with our estimate of this metric. Because I have exactly one data point, there is no math that I can do that will tell me really how precise this rocket's control system is. I'll just have to keep flying it, keep tasking it with waypoints and generating miss distances, and then I'll circle back to this whole precision thing when I have more data. So this flight was very precise. We'll just keep launching it and see what happens. Didn't we have a third rocket launch to talk about? Okay, so Flight Test 5, a little bit of a good news, bad news situation. I did this launch after Flight Test 4, hence the name, and I knew that Flight Test 4 had gone really well. So I tasked the rocket with a waypoint 80 meters upwind, 650 meters in the air. This would give the rocket a little bit more of a challenge, make it maneuver a little bit more, and would really test its guidance and control system. This is also the second Diamond X airframe. This is the one we've been building in that build series, and so this rocket has extra raceway wires to fly with a first stage booster. This was just a shakedown flight testing its hardware and its software on a single stage flight.
Sky is clear. Launching in 5, 4, 3, 2, 1.
Anybody else notice how the rest of the rocket is suspiciously far away? This flight suffered two unrelated failures. The first was this carbon fiber 3D print. This is the wishbone piece that connects our parachute and shock cord to the avionics assembly. This part broke when the parachute deployed, and so the entire avionics assembly fell from over 2,000 feet. This is made out of a very strong carbon fiber polycarbonate, but unfortunately it wasn't printed at 100% infill like it was supposed to, and you can see that it cracked right in the middle of one of the voids in the infill. So that was on me. I should have printed this 100% infill, and I didn't, so this part was weaker than it should have been. This is also a part that a nylon might be really good at because it's more shock resistant, and this is primarily a shock load that it sees when the parachute deploys or when the shock cord snaps taut. Luckily though, it didn't really take much damage. The flight computer was actually still on and transmitting telemetry when I found it, and the battery was just kind of dangling out the front of it. Remember when I said this in the airframe assembly video? The weak links that I designed into these parts are like the arms right here. These are very kind of weak, so if the rocket hits down sideways, the battery will kind of crack off inside of the nose cone, and that should take some energy away from the impact. Well, it looks like that's exactly what happened. The battery mount broke right on these arms right where it was supposed to. The battery cracked off, and it was still connected to the flight computer. Everything else is pretty much damage-free. So all I have to do to fly this guy again is reprint the battery mount, reprint the nose cone, and reprint our wishbone that attaches us to the shock cord, and this rocket should be ready to fly again. The second failure was its guidance system. This wasn't really much of a failure because the rocket did exactly what it was supposed to do, but the guidance system ended up aborting before the rocket reached the waypoint. Okay, remember that foreshadowing thing and how I said something would come up later? It's now later. On this flight, the rocket had a really tough time controlling its roll. Flight 4's waypoint guidance enabled at 135 meters in altitude, but Flight 5's enabled at 400 meters. This meant that the vehicle was already much higher and it needed a much more aggressive maneuver to try to get to its waypoint. As soon as waypoint guidance enables, the rocket pulls almost 7 Gs before tripping that pitch angle limit that I talked about earlier and reverting to abort angle guidance. So I can do 3 things that will help fix this. First, I can enable the control system at an even lower altitude. This will prevent that big initial roll from occurring, and we should stabilize our roll quicker in the flight. Second, I can relax the roll limits before waypoint guidance enables, and this will again help the rocket start guiding earlier. Lastly, I can do a better job of aligning the raceway and fins before launch, and that'll reduce these adverse roll moments that we get. So Flight 4 didn't guide successfully, but this was a good test of that pitch angle limit, and that worked wonderfully. So that's a huge safety system to have on board, and I feel a lot more confident going into the next flights that I know that that safety system works. Speaking of safety, I wanted to take some time here at the end of the video to talk about how you can do rocketry with or without a control system safely and without getting into any trouble. Rocketry is actually a pretty safe hobby, especially compared to something like motorcycle riding. But this doesn't mean that there aren't any risks. In fact, there are a lot of risks. Rocketry is safe because we study and we mitigate those risks. We have strict safety rules and we follow them. A lot of these rules don't actually come from the government. They come from club organizations like NAR and Tripoli in the United States. If you're outside the United States, your local rocketry organization certainly has their own safety code as well. It's really important for you and everyone else that everyone is following these rules, understands the risks, and is taking good steps to mitigate them. If you're flying a rocket with a guidance and control system, you need to take some extra safety precautions. Here in the United States, NAR has some recommendations including increased standoff distances, but a lot of the safety is actually going to come down to you as the engineer. You need to design a system that is redundant where it needs to be, that fails safely, and that's been tested on the ground. Your guidance or control system failing during a bench test is really frustrating. These systems failing while your rocket is flying through the air can get people hurt. A big piece of reducing risk is modeling and simulation, which I have a whole video dedicated to coming out next. Lastly, I wanted to mention not breaking any laws. I have triple and quadruple checked, and I am not aware of any laws in the United States that would stop you from building an active control system for your rocket and flying it. That being said, I cannot speak for any other countries. If you are outside the United States, please check your country's laws to make sure you aren't breaking any of them if your rockets start to steer themselves around. Even if you are allowed to build rockets with guidance and control systems, Obviously, you need to be very responsible with them. Doing something reckless or unsafe with a rocket, intentionally or otherwise, is a pretty good way to get yourself into trouble. Like prison trouble. And if you're ever not sure where the line is, that's probably a good time to not get any closer to it. There's also this confusing mess of export control restrictions, which will vary by country. Many of these rules are vague, intentionally so, and this is one of the reasons why I won't share code or CAD for these projects online or sell them to people. In many respects, the line between a rocket and a drone continues to get blurrier, so the best advice I can give you is to learn the rules for wherever you are, follow them as closely as you can, and always keep safety at the front of your mind. Okay, we can now task rockets to waypoints. What is coming up next? We're going to keep flying Diamond X. I really want to try some further upwind waypoints to try to keep those recovery distances short. I've also been working through booster integration, and we should have our first Diamond X Block 3 flight with a booster in the next few months. You guys may have seen me posting some stuff about Hatchet. This is the rocket/drone thing I'm building with a ducted fan. Hatchet's being put together right now, and I've got its propulsion and control assembly prototype built. So if you're interested in that one or any of these future projects, make sure you're subscribed, and I'll see you guys in the next one.